The nonlinear geophysics focus group of AGU is composed of transdisciplinary group of scientists from virtually every discipline represented by AGU, who use the mathematical tools and approaches of chaos, fractals, scaling, self-organized criticality, nonlinear dynamics, and complexity to analyze and model Earth science systems. If you are working in this field, those sub-disciplines I just mentioned, or you would like to learn more about our group, we invite you to join us. And you would do that by going to the AGU booth and asking for membership services and adding us as one of your affiliated sections or focus groups. And I'm sure they will be very happy to help you. That way, you will receive our newsletters and be better able to follow what this group is doing within AGU. We are a young group. This is the second Lorenz lecture. As John alluded, last year the first one was given by Benoit Mandelbrot, the father of fractals. Today's lecture is to be given by Don Turcotte, one of our own, and one of the best versed in the broad application of nonlinear geophysics to the earth sciences. Don received his bachelor's degree, I know he hates this sort of thing, from Caltech in 1954. He received his master's in aeronautical engineering from Cornell in 1955. Went back to Caltech and received his PhD in 1958. He joined the faculty of Cornell in 1959, where he remained until this month. He served as the Maxwell Upson Professor for many years and was a long-time chairman of the Cornell Department of Earth and Atmospheric Sciences. After 40-plus years at Cornell, Don has retired and is now a newly minted faculty member at the Geology Department at the University of California, Davis, beginning this week. He's a member of the National Academy of Sciences. He was one of the first to appreciate the importance of fractals to the earth sciences and is a leader in this field. He's the author of a well-known book called Fractals and Chaos in Geology and Geophysics, which is a compendium of insights, understanding, and applications in the earth sciences. It is with great professional pleasure that I give you Don Turcotte, whose lecture tonight is entitled Self-Organized Complexity in Geophysics.
Thank you very much, Chris, and it's a great honor and a pleasure to be the second Lorentz lecturer, and I'll return to that a little bit as I go along. But first, I just would like to thank so many people who have worked with me over the years. This is a list of people who have co-authored papers in this general area with me over the last 18 years or so, students and postdocs and professional colleagues. Now, so we have sort of, over a period of time, used this name, self-organized complexity, to define the sort of things that I want to talk about. And the best example is really fluid turbulence, which remains one of the great unsolved problems in physics. It has scaling relationships, such as I will discuss as I go along. It also has a completely understood deterministic root, the Navier-Stokes equations. Yet despite all the massive computation available, we cannot solve problems in fluid turbulence. Now, obviously related to this concerns weather, climate. The Earth's magnetic field is clearly a turbulent problem. Mantle convection is probably turbulent, but we don't have the database to really define that, but it's almost certainly turbulent. Seismicity and tectonics are very closely related. Drainage networks and landforms are another example. So let's look at some of the roots of this class of problems. Now again, as we look here, we see the first was deterministic chaos, which Ed Lorentz certainly discovered. The basic fact that deterministic equations, such as the equations of thermal convection, gives stochastic or statistical solutions with a very set rules. It's very universal. So there's period doubling root to chaos. There's positive Lorentz exponents. Nearby solutions diverge exponentially. Then the second major step forward was the concept of fractals. This brought together many different previous observations, some of which I will discuss in a few minutes. And Benoit Mandelbrot talked about those as he gave his lecture here last year. Now, still, in terms of statistics, there is a lot of controversy as to the role of fractals, because the fractal distribution, the power law distribution, does not really converge in a statistical sense. So it's really not an accepted statistical distribution, yet is extremely useful, and probably, after Gaussian distributions, is the most important statistical distribution in natural phenomena and in many other areas. The third major step forward, in my point of view, and I think many others, was the concept of self-organized criticality, put forward by Per Bach and his colleagues in 1988. Very unfortunately, Per Bach died on October 16th of this year, so he could very well have been a future lecturer, or even he instead of me this year, but that unfortunately will not take place. And I will discuss self-organized criticality as we go along. Now, what about predictability? I mean, we would like to predict the weather, and as everyone knows, you can make weather forecasts, but they're certainly not perfect. And this is intrinsically related to the concept of deterministic chaos. Even if we had absolutely all the information on the system, we still could not make exact forecasts. On the other hand, we can make statistical forecasts. If you look at the paths of hurricanes on the Weather Channel, sometimes the forecasts are quite good, and other times they're very bad. And this can be put forth in what's known as ensemble weather forecasting, where you basically either use a whole range of models, and if they all make the same prediction, you have confidence. If they make very different predictions, then you don't have confidence in what's going to happen, say, on the path of the hurricane. Now, the sort of more less understood question is the basic forecasting of earthquakes. I'm not sure what we would do if we really could forecast earthquakes, evacuate Los Angeles or something like that, but it is certainly, at least to indicate times of high risk, would have great societal benefits, I would think. Now, there are indications that we can make progress on this in the same sense as ensemble weather forecasting, but any question of exactly forecasting earthquakes is no more possible than exactly forecasting the weather or the direction of a hurricane. Now, I would like to talk a little bit about 3 different problem areas here, and they're listed here. And I would like to emphasize, in each case, observations and the implications of what we're talking about relative to these observations. I would like to start with drainage networks. Now, drainage networks and the Horton-Strahler statistics of drainage networks were recognized by Mandelbrot to be a key example of fractals. So the evolution of the drainage networks is a classic example of this self-organization that is the subject of this talk. Now, I just would like to briefly discuss some of the basic aspects of this branching. And it's very interesting, the history of how this developed. For example, Horton-Strahler just assigned the order of different streams. The first order stream is the smallest stream. 2 first orders make a second, etc. However, it was not realized then that there are different kinds of first order streams. There are also first order streams that go into second order streams, and this is basically side branching. And it was recognized by Takenaga that this side branching has self-similar properties and is very diagnostic of alternative models. And also, as is in the case of some of these examples that I want to talk about, it has a great universality, that this kind of side branching occurs in many different areas, many branches of biology. Our own bodies have this kind of side branching, for example, in the cardiovascular system, the bronchial system, etc. There seems to be an optimal form for this network that drainage networks have evolved to, and that the natural selection in biology has also evolved to. Now, so I would like to just look a little bit at this. So these are just, as you all recognize, a set of different drainage networks. In looking at this kind of approach to science, we tend to look at the statistics, and there's a fair amount of criticism of doing this, that the statistics may not be diagnostic. But I think we have to combine the physical processes approach with the statistical approach in order to get a better understanding of where we're trying to go in understanding natural processes and biological processes. Now, I don't want to go in the details of the side branching too much, but I would just point out that what this says, this kind of statistics, what we have here is that for example, each second order stream has 1 first order stream coming into it. Each third order stream has 1 second order stream coming into it, etc., etc., etc. And then there's a power law relationship that, for example, 1 first order stream goes into a second order stream, 2 first streams go into a third order, 4 first orders go into the fourth order stream. And this is what is shown here. And Scott Peckham, who did this work, created a program called River Tools that you can use to automate this whole process. It's a commercially available program, which is very useful. Now, I want to just return for a moment that Peckham did this work totally independently of, and wasn't aware of Takenaga's work, but a reviewer was, despite the fact that Takenaga's work had never been referred to virtually in some 20 years after it was published. And so the appropriate credit was given there. However, the same schemes were developed totally independently in the physics literature, and I'll come back to that in a minute. So, for example, here we have roughly, say, for example, 10 first-order streams going into each third-order stream, because the difference is, if the difference is 3, so 10 first-order into 4, 10 second-order going into 5, etc., etc., and then we're getting up to the level of 1,000 first-order streams going into a ninth-order stream, such as the Mississippi River. So all this scaling really works very well. And then if I put this view graph back up, which is the example of these drainage networks, and I put up a photograph of, in this case, some leaves, as on trees, what happens is that the statistics of side branching and the overall branching of the vein structure here is identical to that, absolutely identical, same ratios, same everything. So that there is a process in the genetic coding that creates these leaves, whatever that coding might be, that creates the statistics of this optimal system for delivering nutrients to the leaf structure, which is the same as the kind of optimal system that you get here as the Earth has developed to have all these drainage networks. Similar drainage networks occur on Mars. So that's you need to apply these kinds of studies to work on Mars. And then in the physics community, Len Sanders and Witten developed the concept of diffusion limited aggregation, which is a large subject in physics in which you have random walkers that randomly walk across the surface, taking steps, and when they hit this network, the network expands. So that the expansion of this network gives this kind of a typical growth pattern. And as I pointed out a little bit ago, it was discovered that this growth pattern has exactly the same kind of structure as the drainage networks and the leaves. So that the entire side branching structure of that picture is identical to the side branching structure of the leaves and the drainage networks. And Osadnik published the results on the side branching of DLA in 1992, totally independent and not recognizing the work of Tokunaga. There's still lots of work going on DLA, and it's fair to say that DLA is not understood. It's a game, it's a computer game that delivers these structures, but the sort of the philosophical underlying what's going on is not really understood. You cannot do it really in terms of continuum equations or classical applied mathematics, which you know, some of you may have bought Stephen Wolfram's book, all 1,200 pages of it, and that's sort of the message that he is delivering. Okay, so let me move forward into the second subject of the three that I would like to discuss. And this has to do with time series. Now, one of Benoit Mandelbrot's major contributions was to basically defining what self-affine fractals are. Self-affine fractals are basically associated with these self-similar time series. And they are defined in terms of this relationship, which has the power spectral density, which is like the square of the Fourier coefficient of frequency f, the square of that coefficient has a power law dependence on the frequency to the minus beta power. Okay, so these, now this is one I want to show. All right, so just briefly, let me just review a little bit about time series. And time series are important in many, many different areas. For example, the stock market and other things like that. Now, a Gaussian white noise is specified if you specify the standard deviation and the statistical distribution of values, which would be, for example, Gaussian. So each time step here, 512 time steps, is assigned a randomly generated number based on a Gaussian distribution so that adjacent points are totally uncorrelated. There are 4 realizations here, and this is what is a Gaussian white noise. Now, if you take the running sum of a Gaussian white noise, you get a Brownian walk. A Brownian walk is not stationary. The standard deviation grows with the square root of the number of steps. Now, following the work of Henry Hurst on rescaled range approaches, which were studied primarily in hydrology, Mandelbrot and with his colleagues came up with the concept of fractional noises on the left and fractional walks on the right. So that you have your white noise, you sum it up to give Brownian noise, and then you have fractional contributions. This is a 1 over f noise with beta equal 1, and that is the transition from a set of stationary fractional noises to the non-stationary fractional walks. The walks have a drift to them, and the noises do not have a drift. They have a well-defined mean and variance. So let's look at a couple of examples. And these examples are work done by John Pelletier. And the first example I would like to give is the Earth's magnetic field. So these are the observations on the strength of the Earth's magnetic field, the virtual axial dipole moment, as a function of time measured backwards in the past. So the last magnetic reversal occurred about 700,000 years ago, and you can see the various flips that occurred here. Now, if you do a spectral analysis of that, you get the results that I show here. And basically what you get is a classical 1 over f noise. So the noise in the Earth's magnetic field, I would make the argument, is basically what is happening. This is the noise generated by the turbulent convection in the Earth's core. And it's the noise that really is the key to what is happening. Now, if you generate a synthetic 1 over f noise with positive polarity, once in a while the amplitude gets so high that it crosses 0. This is a case in which you have the 1 over f that's measured for the Earth's field. It has the correct amplitude, mean amplitude, but once in a while the natural fluctuations go to 0 so that it flips. So if you just look at when it flips, you get this result, which basically statistically satisfies the reversal statistics of the Earth's magnetic field. So if you look at the frequency length of reversals, there is a region of reasonably decent power law scaling consistent with the 1 over f result. And in fact, if it were a 1 over f to the 1/2 or 1 over f to the 3/2, you'd get a very different slope. So this is an independent confirmation of this concept that is the random fluctuations of the Earth's magnetic field that leads to the reversals. And in fact, that's exactly the same thing that happens in the Lorentz equations, or the Riccataki dynamo, which was set forth as a simple model, which also had these flips. Those were low-order systems, so therefore the Lorentz equations yield solutions that are quasi-periodic, but they flip as the amplitude crosses zero. The solutions to the Lorentz equations flip just like these do, but here, instead of the quasi-periodic of the low-order system, we're basically using a fractional noise, a 1 over f noise, to get this flipping. So I think that provides a reasonable explanation. We don't have the theory essentially to understand why the Earth's magnetic field has such a simple statistical behavior, but that's obviously a goal. Now, this is work also done by John Pelletier, and this has to do with global temperature. So that this is the global temperature inferred from the deuterium concentrations in the Vostok ice core. And you can see the ice age going back the last 10,000 years or so, the ice age that the colder temperatures prior to 10,000 years ago. And you can see that, again, so a great deal of effort has gone into studying this kind of work, particularly with global warming. But again, I'd like to make the argument that the noise is an extremely important component of these kinds of problems and should not be just neglected. What John used that data, but he also used data from instrumental records. These are records from central England that go back 250 years. So this is the noise record of the shorter periods. And then he did fast Fourier transforms and found the noise components. Now embedded in this analysis are the Milankovitch cycles of the ice ages, which are up here in this range. But you have this white noise component for periods longer than 50,000 years. And then for periods between 50,000 years and 2,000 years, you have a 1 over f noise. So you're getting a drift, 1 over f squared. So this is a Brownian walk for this range of periods or frequencies. Then between 2,000 years and 1 month, you have a 1 over f to the half power. And this is a very universal type of behavior that leads to a Hurst exponent of 0.7. So Henry Hurst found this kind of behavior in his work, or earlier work, in many different areas, as I will point out in a moment. So this is basically can be relatively easily understood. This drift is when the temperatures in the ocean drift. The frequencies are so slow that the atmosphere and the oceans are coupled. At higher frequencies, the temperature of the atmosphere is buffered by the oceans, and therefore your fluctuations are damped out, and you have stationary signals here, whereas these are non-stationary. And then for very short periods, you get this transition to non-stationary behavior in the continents, but in the oceans you continue to have the 1 over square root of f behavior. Now, in fact, I would say that any global climate model should satisfy this behavior, because if it doesn't do this, it's not really working. Now, the only case we could find that somebody had actually tried to do this with global climate models was in this paper by Manabe and Stauffer. And you see there's very little correspondence. In this range of frequencies, you should get 1 over f to the half power, and the actual GCMs are giving you something much more like white noise. So they basically, at this point, I don't see that they're satisfying this test of their applicability. Sorry. Now, if you look at solar radiance with different frequencies coming in, you get this same transition for solar, the output of the sun. And in fact, if you look at semiconductors in the laboratory, the noise in semiconductors, you get the kind of transition shown here, which is similar to what we see in the atmospheric temperature. And the physics of this basically the same. It's the role of the thin sheet coating with a substrate that buffers it. So it's basically the thin coating is the atmosphere, and the oceans are the buffer that stabilizes the system. Now, I said that 1/2 is quite universal. If you look at a variety of river discharges, you tend to get this Hurst exponent of 0.7, a beta of 0.5, 1/2. Or if you look at tree ring records, you get the same thing. So again, this is a kind of noise that is quite universal. Now, I don't want to claim that all this is perfectly understood, but in fact, what you do have is solutions of Langevin equations. In other words, stochastic differential equations give this kind of behavior. So there are physical ways to get this kind of behavior using classical applied mathematics in terms of stochastic differential equations. You can also use cellular automata to get this kind of behavior. Okay, so the third and final thing that I would like to discuss is self-organized criticality. Now again, there is no question about who invented self-organized criticality, per Bach and colleagues. There's a question as to its utility, but that I will come to. So many of you are familiar with the concept of the sand pile model. You take a square grid of cells, the boxes. You randomly throw particles at the boxes. When a cell has 4 particles, you redistribute them to adjacent boxes, and that can create so-called model avalanches as the particles create further instabilities, and these can cascade into very large avalanches involving many boxes. If you look at the statistics of the number of boxes involved, or some other statistics, you find that you get this fractal behavior, that the number of events of a specified size, the size is the number of boxes. So here are the number of avalanches with just 1 box participating. Here is the number of avalanches, say, with 10. So there's about 100 with 10. And this is, the characteristic of these solutions is that the slope is -1. So an order of magnitude down this way is an order of magnitude this way in terms of area. I might digress just for a moment that although these 3 concepts that I've described, fractals, deterministic chaos, and self-organized criticality, have great universal application today in many branches of the literature, in essence, all 3 were created in geophysics in a generalized sense. Mandelbrot's first paper on the length of the coastline of Great Britain was basically geomorphology, if you like, the length of a rocky coastline. His work with Wallace on the self-affine fractals, as I've described, was basically based on hydrology. It was published in Water Resources Research. Similarly, per Bach's original applications for this was to Gutenberg Richter. So all of these concepts came out of earth science problems in the earth sciences. And of course, that's not strange because, you know, every geology student knows that you have to put an object in a picture of anything in geology, and that's the epitome of scale invariance. And the epitome of why these things work this way is basically scale invariance. If you don't have scales, the only thing you can get is a power law. You cannot, everything else is defined by some kind of scales. So scale invariance in itself is sufficient to give you this kind of behavior. Now, there have been a lot of arguments about the application of things like this, the sand pile model. But working with Bruce Malamud, we have looked at, and also Fausto Gazzetta, we have looked at real landslides. So these, we are putting forth the argument that there is a universal frequency size distribution or statistical distribution for actual landslides. And we basically look at the 10,000 landslides generated by the Northridge earthquake, 8,000 landslides generated by hurricane in Guatemala, and an Umbria snowmelt event with about 3,000 landslides. And we show that we basically have this universal statistical distribution of landslides that says that all landslides, triggered landslide events, have the same mean area, the same distribution, if we believe this. Now, there's more work to be done, but I think it's rather convincing evidence. And this is a linear plot, and this is a log-log plot. And this straight line is a so-called fat tail, a basically power law tail or a fractal tail. And fractals have to be terminated. They cannot go from 0 to infinity because they don't converge statistically. So there has to be terminations. But these fat tails are very important in many different applications. Next, I would like to go to a second model that gives you self-organized criticality, so-called, which are the slider block models. And there are hundreds of papers in the literature on slider block models. Now, this is different than the sand pile model in that this is completely deterministic. In other words, the equations that govern the slip of these slider blocks, they have a frictional interaction with the surface. They are connected to each other and to this driver plate by springs. So you just pull the driver plate over the surface, and these blocks stick and slip. And sometimes you get a small slip event, just one block, and sometimes you get slip events that include multiple blocks. Again, they basically have this same power law distribution. So I will show you that. So again, once again, the slope is near 1. This is the number of events versus their size. The area is the number of blocks that participate. So these are 1-block slip events. These are 10-block slip events, 100-block slip events. And the stiffness determines how big the biggest slip event is. That is the ratio of the connecting to the driver spring constants. However, I think I would prefer to emphasize sort of the philosophy of this problem, because this is a really nice problem to illustrate some of the connections between the three aspects that I've discussed. The statistics here are fractal. But if I take just 2 blocks, if I take 1 block, it's very boring. You can do this in your, when you're teaching. You pull a block with a spring, and it just does periodic slip events. The time between the slip events constant. So this is the so-called the characteristic earthquake model. The time between earthquakes is just a set time, and earthquakes on the San Andreas, say, occur every 300 years. However, if you make 2 blocks, it gets very interesting. Because if you do this with 2 blocks, and if you break the symmetry in any way, different masses, different spring constants, you get chaotic behavior. In fact, you get exactly the same chaotic behavior for this system that Lorenz got for his system or that May got for the logistic map. These systems all exhibit exactly the same behavior in many different ways, not just sort of qualitatively. They have the same period doubling route to chaos. They are defined by the behavior of the Lyapunov exponent. So these problems, some are stochastic, some are non-stochastic, have very, very similar behaviors. Now, the final example I would like to, well, I'll go one step further before I'm sorry. Of course, the motivation of the slider block models was Gutenberg Richter. And this is worldwide Gutenberg Richter. The number of earthquakes with rupture areas greater than this or magnitude. It's been shown that Gutenberg Richter is a fractal relationship between the rupture area of the earthquake and the number of earthquakes. So that if you look, for example, in Southern California, you find that in years when you don't have aftershocks, you get exactly the same Gutenberg Richter relationship for the earthquakes year after year after year. So the Earth's crust has this noise. The smaller earthquakes, say below around magnitude 5, they're just a noise. And of course, you might like to use the small earthquakes to predict big earthquakes. And if you'd think, as the stress built up in California, that the number of earthquakes would change. But what makes earthquake forecasting or prediction so difficult is that they don't. That year after year, they don't change. And there's just this noisy background there that prevents you from inferring the state of stress in California from this. However, you can use the so-called A value, the level of the seismicity, to make hazard forecasts. So this is just a color-coded map of the number of earthquakes with magnitude greater than 4 from the worldwide data center, and that's color-coded, and you can sort of you can make an earthquake forecast this way, or a hazard forecast. Now, the current hazard forecasts are more sophisticated than this, but looking at the local Gutenberg Richter is certainly an important input into the USGS hazard forecast or anybody else's hazard forecasts. And then that includes some arbitrary combination of other factors like capable faults and things like that. But this is very cut and dried, and at least to a first order. For example, it tells you that the probability of an earthquake in Southern California is about a factor of 10 greater than the probability of an earthquake in the New Madrid region of Missouri and that general area along the Mississippi River. Okay, so as I said, I've jumped to a little bit. I wanted to talk about one of my favorites a little bit, and that's the forest fire model, and this will conclude what I have to say. So the forest fire model is conceptually very simple. You have an orchard, which is a square grid of trees, and you randomly plant trees on unoccupied sites. And after so many tree plantings, you drop a match. And the resulting fire burns all the adjacent trees. And so that you have this kind of a situation. This is a typical run on a 128 by 128 grid. And examples of different small fires, bigger fires. Sometimes you have a sparse forest, and other times you are growing your forest and you can generate very large fires. Now again, if you look at the frequency size distribution of fires, you get essentially the same slope. This is the number of fires with an area, which is the number of burnt trees. Again, you have this 1 over area behavior, just as you did for the two previous models that I discussed, the sand pile model and the slider block model. Now, a few years ago, Bruce Malamud and I published a paper in Science that basically argued that real forest fires behave the same way. That and these were 4 different basis statistical data sets that we used to show this power law behavior, looking at the area of the fires and the number of the fires, and again, you seem to get this power law. Totally independently, Minich from University of California, Riverside, made a comparative study of forest fires in Baja California, below this line, compared with the forest fires around San Diego. The maps are shown here, Baja California, near San Diego. And you can just see at the map of the fires that the whole character looks very different. And he basically made log-log plots, although he was totally unaware of our work and really unaware of what fractals were. And he found that, for example, looking down here, in Baja California, you have a lot more little fires and few big fires. And then in Southern California, you have a lot fewer little fires, but you have a lot more big fires. So this is, the whole controversy of how you manage forests are related to this. Both look like reasonably straight line power laws. But it depends whether you put out the fires or you don't put out the fires. In Southern California, there's great effort to put out the fires, whereas in Baja California, relatively little effort is made. So again, this is sort of a, I would argue that there is real utility to these models, and there is a universality of these models, and the other concepts, the 3 concepts I've discussed here, that they have very broad utility, particularly in biology, but also in other branches of science. For example, the evolution of the Internet is looked upon as a self-organizing critical situation. There are studies of arrhythmic heartbeats that use concepts of fractional noises. And the concept of self-organized criticality is applied to many things like epidemics and other things. So I've tried to give you a flavor of sort of this kind of approach to science, which is somewhat different. In general, you cannot do this kind of science with classical differential equations, linear equations, because you just can't get any of this. So you have to have nonlinearity in general. You may be able to do it with stochastic differential equations, but solutions with strong nonlinearity, like the Lorentz equations or the slider block equations, can give this kind of behavior. So this is an aside from what would be classical geophysics. The classical equations, Laplace's equation, the heat equation, the wave equation, are not going to give you solutions of this style. It's really a kind of different physics. And, I don't want to push Stephen Wolfram's point of view too hard, but it's essentially the same point that he is making in his book. So with that, I'd like to stop and thank you very much for your attendance and your attention, and appreciate it very much.